for a function to be continuous at x is equal to a, three things have to happen. The limit as x approaches a on the function from the left has to equal the limit as x approaches a from the right. And it also has to be equal to f at a at that point. If all three of those aren't equal, then it's not going to be continuous. So in order to find out whether a function is continuous or not, you've got to find all three things and see if they're all equal or not. If they're not, then you might get a removable discontinuity, a jump discontinuity, which we've already looked at, or an asymptotic discontinuity. So let's look at g at x here. Is g at x continuous at x is equal to 1? Well, our job is to find out all three of these things. So the limit as x approaches 1 from the left of this function, g at x, is going to be equal to, who am I going to sub in for here? I'm going to sub in for this function here because from the left of 1 is there. So it's going to be negative 1 squared, which is negative 1. If I take the limit as x approaches 1 from the right of g at x, which function am I going to sub into? It's going to be this one again. So, or this one. It's going to be 1 over 1 minus 2, which is negative 1. Now, if I find g at 1, that has to be equal. So far, so good. But g at 1, when I sub in, of which function am I going to sub into? This one or this one? It's going to be this one because it has the equal sign. So I'm going to get negative 1 squared, which is, of course, negative 1. It turns out that all three of those are equal. And because all three of those are equal, it is continuous at x is equal to 1. Can I say that the function is a continuous function? That implies that it's continuous everywhere. We've only tested for x is equal to 1. It's not going to be continuous everywhere because if this function here is a reciprocal function and it has an asymptotic discontinuity, it has an asymptote at x is equal to 2. That's a restriction there. So you can see that as you approach 2 from the left here, you get negative infinity. If you approach 2 from the right here, you're going to get positive infinity. So they're not equal. And if you try to find g at 2, you wouldn't be able to because it's not even defined there. So this is a an asymptotic discontinuity at x is equal to 2. Let's look at this example. Find the value of k so that f at x is continuous. So now we don't know whether this is going to be continuous or not. We want to make it continuous by finding the values of k. Remember that for something to be continuous, the limit as x approaches a from the left has to equal the limit as x approaches a from the right. So let's write that. The limit as x approaches, where's the break here? It's at 1 from the left of f at x has to be equal to the limit as x approaches 1 from the right. I'm going to sub in then for 1. Direct substitution is how we evaluate limits algebraically first. So when I put in 1 here, I get the square root of k minus 1. When I put in 1 on the right here, I get 1 minus k. Solving for k, solving a root equation, let's get rid of the root by squaring. So we get k minus 1 on the left. And if we square a binomial on the right, we get 1 minus 2k plus k squared. We're solving a quadratic now, so then we move everything to one side. 0 is equal to k squared minus 3k plus 2. Solve the quadratic by factoring. So we get k minus 2 and k minus 1, two numbers that multiply to 2 and add to negative 3. So what's our final answer for k? K can be 2 or k can be 1. Both of those values would make this function continuous.